Okay, this video is about the factor theorem, and you're already familiar with some of the factor theorem probably if you're watching this video. For example, when we do quadratic equations, if I'm trying to solve this equation, then I factorize the left-hand side here to get x plus 9 times x plus 3 equals 0, and you say that because x plus 3 is a factor, that means that x equals minus 3 is a root. Because x plus 9 is a factor, x equals minus 9 is a root, because that would make this bracket 0 or this bracket 0. And there are two roots of the equation. And what the factor theorem says is that that's also true in reverse. So if x minus 3 is a root of this equation, then the expression must have x plus 3 as a factor. If minus 9 is a root, then it must have x plus 9 as a factor. And the nice thing about this is it means that I know there are no other roots. So for example, it can't be that x equals 2 is another root, otherwise this would also have to have x minus 2 as a factor. And this result can be really useful in factorizing higher order polynomials. So for example, let's take the polynomial, cubic polynomial here, x cubed minus 6x squared plus 11x minus 6, and I want to try and factorize it. I could try x equals 1, and when I plug x equals 1 in here, what do I get? I get 1 cubed minus 6 times 1 squared plus 11 times 1 minus 6. Right, that's 1 minus 6 plus 11 minus 6, that's 12 minus 12, that's 0. So 1 is a root of this equation if I put that equal to 0. So what that means is that this expression must have x minus 1 as a factor. It's going to be x minus 1 times something. And when I put x equals 1 here, I get 0, so it's 0 times something, so that's the same as all of this, which is 0. Okay, so it makes sense. So we can try some other numbers. I could try x equals 2. Right, so 2 cubed minus 6 times 2 squared plus 11 times 2 minus 6, and see what we get. Well, I get 8 minus 24 plus 22 minus 6, and that's 30 minus 30, that's 0. Being very lucky here. Well, I've designed it to be lucky. So x equals 2 is a root of the equivalent equation, so that means that x minus 2 is a factor. Cubics have 3 factors. Now I could keep looking, or I could try and find the other one. Actually, if you thought about multiplying this out, minus 1 times minus 2 times whatever goes here must give this, so actually the last one is going to be minus 3 probably, but let's just check. So when I substitute in x equals 3, I get 3 cubed is 27 minus 6 times 3 squared, so that's minus 6 times 9 plus 11 times 3 is 33 minus 6. 6 times 9 is 54, so that's minus 60 plus 60, so that is 0. So my final factor is x minus 3. Now, if you tried any other number in this one apart from 1, 2 and 3, you would not get 0, right? I've designed it so that 1, 2 and 3 worked. Usually, it's not as easy as that, right? You might have to try some more numbers before you find it. But that gives us this nice way of factorizing polynomial expressions, because if a value is a root of the equivalent equation, then x minus that must be a factor. Now, it's not always as easy as just 1, 2 and 3, although if you're in a non-calculator exam and you're doing a question where this is the sort of thing you need to do, then you can expect them to put in a fairly small number, something between minus 5 and 5 certainly, as one of the factors, probably even smaller than that. There's usually plus or minus 1 or 2 as one of them. But if you do have a calculator with you, you can do this a bit more quickly, because I could just try all those values very quickly and see. So if I type in here in the function mode, so I've just gone here mode 3 for the table mode that gives me this function, and I type in x cubed minus 13x squared plus 6x plus 72 here, which is the function, and I could say start at minus 5, end at plus 5, and do it in a step of 1. So that's going to substitute in all the values between minus 5 and 5 and tell me what the the output is. So they're not 0, not 0. There's one that's 0. So x equals minus 2 works. And no, that's just x equals 0. There we go. Another one where y is 0, so that's x equals 3. And that looks to be it between minus 5 and 5. So I found two factors here. So it's x minus minus 2, which is x plus 2, and also x minus 3. It's a cubic equation, so I'm expecting another factor here then, a linear factor, so I've got a cubic order here. And I can find the third one pretty easily here because 72 it has to be 2 times minus 3 times this last value. So if I do 72 divided by 6, that gives me 12. So actually this must be x minus 12. And if you check, actually I could just get this to substitute in the value 12 for me quickly. Yes, 12 is the other one there. So that's the crux of the factor theorem. This is sometimes stated a little bit more formally. I could write this down and say something like x minus a is a factor of the polynomial f of x. That's one statement that we're using. And the other one is that f of a is 0, i.e. a is a root of f of x equals 0. And what the factor theorem says is that these two things are equivalent to each other. Okay, it says that if this is true, then this is true, and if this is true, then this is true, i.e. if I substitute in a value I get 0, that means that x minus that value is a factor. Similarly, if x minus a certain value is a factor, then that number will work in the polynomial. Sometimes you'll get exam questions and they look a bit like this. It says, x minus 2 is a factor of this expression, so can we find a? So there's an unknown value in here, a, but because x minus 2 is a factor, what that means is when I substitute 2 in here, using the factor theorem, I must get 0. So 2 cubed plus 3 times 2 squared minus 2a plus 7 must be 0. So that's 8 plus 12 minus 2a plus 7 is 0. We've got a simple equation in a that we can just solve. So I've got 19, 26 looks to be equal to 2a, so a is equal to 13. So there's a simple application of the factor theorem there in a kind of exam style question. But the main point is you get how it works from those previous examples, and once you get that idea, these sorts of things will be fairly easy. The factor theorem often goes with something called the remainder theorem. They're very similar theorems that say just slightly different things. So if you get this, I would say go on to the remainder theorem. I'll make another video about that.